In this video, I'm going to talk about how we can apply the principle of linear and angular impulse and momentum to a rigid body and understand the condition for conservation of linear and angular momentum. From particle kinetics, we learned the linear momentum. The vector of mass times velocity is called the linear momentum and denoted as L. This vector has the same direction as a velocity. By using the linear momentum and using the equation of motion, we find the principle of linear impulse and momentum. And the v2 is related to the final velocity of the particle at time t2, and the v1 is related to the initial velocity of the particle at time t1, and the force acting on a particle as a function of the time. Also, from particle kinetics, we talk about the angular momentum of particle about a specific axis. The angular momentum h calculated by two methods, a scalar method and the vector method. And mass times velocity is meaning the linear momentum times the d. We can find the angular momentum, and the d is a perpendicular distance from O to the line of action of linear momentum. For the vector formulation, we have cross product of r and linear momentum. We proved that the resultant moment acting on a particle about point O is equals to the time rate of change of the particle's angular momentum about point O. By integrating between the time interval t1 to t2, we found the principle of angular impulse and momentum. The first and the third term of this equation represent the angular momentum of the system at the time t1 and t2, and this term is represent the angular impulse. In case of 2D is meaning if the motion happen in the xy plane, it can be applied as a scalar equation. Apply as a scalar equation using component about the z-axis. Now we have to apply the linear and angular momentum in the rigid body. The linear momentum of a rigid body is defined by mass times velocity, but the velocity at the center of mass. This equation states that the linear momentum vector L has a magnitude of equals to the mass times velocity at the center of mass and the direction defined by Vg. The angular momentum of a rigid body is defined by this equation, and as you can see, the angular momentum about point G or the center of mass equals the moment inertia of the center of mass G times omega. Remember that the direction of HG is perpendicular to the plane of rotation. And as you remember, when we have rigid body, we have three types of the motion. When we have translation on the rigid body, is meaning when a rigid body undergo rectilinear or curvilinear translation, and therefore we don't have any angular velocity and omega is 0. When the omega is 0 is meaning the angular momentum is 0. Therefore, the linear momentum at the center of mass is equals mass times Vg, and the angular momentum at point G is 0. When a rigid body has a rotation about a fixed axis. Look at this figure. When a rigid body is rotating about a fixed axis through the point O, the body has linear momentum and also angular momentum about point g. And we can write the linear and angular momentum about point g. But it's sometimes inconvenient to compute the angular momentum of the body about the center of rotation. If we want to find the angular momentum about the center of motion, is meaning point O, we have IO times omega. The IO is the moment of inertia of point O. And the last type of the motion on the rigid body is a general plane motion. When a rigid body is subjected to general plane motion, is meaning both translational and rotational motion, we have the linear momentum and angular momentum. And these two terms, we can find it about the point G. And L as a linear momentum equals mass times velocity at the center of mass, and the angular momentum hg equals the mass and the moment of inertia of the rigid body at the center of mass times omega. The angular momentum about point A is found by ig times omega plus the linear momentum of the object, the rigid body at the center of mass, make a moment at point A. For this reason, we have mass times velocity at the center of mass times the d. The d is the perpendicular distance from any arbitrary point, like as point A, to the any point along the action of the linear momentum at point G. Based on this information, now we can write the principle of impulse and momentum. Again, look at the particle motion by using the equation of motion and also the equation of motion and also the equation that related to the kinematic equation, we can find the linear impulse and momentum for the rigid body and also the angular impulse and momentum about rigid body. As you can see, for the first equation, again, the velocity is found at the center of mass. And for the second equation, is meaning the angular impulse and momentum, we have to, if we write about the center of mass, we have to use the moment of inertia for the center of mass, or the G. If the rigid body, if the motion of the object occurring in the xy plane, the linear impulse and momentum can be applied to the xy direction, and the angular momentum and impulse is applied about a z-axis that passing through any point, like as point G. Therefore, the principle is three scalar equation describing the planar motion of the body. As you can see in this figure, we have two linear impulse. We have linear impulse in the xy plane, and also we have angular momentum about the point G that happen about the z-axis that passing through the point G. Now we can write these three scalar equations. For conservation of momentum, this is the equation of linear impulse and momentum. If the sum of the linear impulses acting on a rigid body or a system of rigid bodies is zero, all the impulse terms are zero. Therefore, the linear momentum for a rigid body is constant or conserved, and we have the linear momentum at time 1 equals the linear momentum at time t2. This equation is referred to as the conservation of linear momentum. The conservation of linear momentum equation can be used if the linear impulse are small or non-impulsive. For example, when we have collision or impact, we can use the conservation of momentum or conservation of angular momentum. For conservation of angular momentum, this is the equation of the principle of angular impulse and momentum. If the sum of the angular impulse due to the external forces acting on a rigid body is zero, all the impulse terms are zero. Therefore, angular momentum is conserved, and the resulting equation is referred to as a conservation of angular momentum. If the initial condition of the rigid body is known, conservation of momentum is often used to determine the final linear or angular velocity of a body just after an event occurs. Again, this equation is suitable when we have impact or collision between two rigid bodies. Let's look at two examples. Disk A has a counterclockwise angular velocity of omega 0 at time 0, and disk B is stationary. Disk A is moving into contact with disk B. As a result of the friction, the angular velocity of disk A decreased and the clockwise angular velocity of B is increased until there is no slip between the disks. What are their final angular velocity? Is meaning omega A and omega B. And the moment of inertia of the disk are IA and IB. Now we have to find the omega A and omega B based on the radius of the two disks RA and RB, and also moment of inertia IA and IB, and omega 0. As you can see, this is the disk A. The disk A is rotating in this direction, and the friction opposite of the motion. For this reason, for disk A, the friction is downward. Based on the Newton third law, when we have action and reaction. At the reaction has the same magnitude but in opposite direction. So the friction force that apply on the disk B has the same magnitude of the F, but the direction is upward. And there is no any other force that apply on this to this that make angular momentum on the disk. By applying the principle of angular impulse and momentum to disk A from time 0 to time F, the time F is the time that sleep stop, okay? So this friction force is make angular momentum at center of the disk A, but as you can see, this one as a clockwise. For this reason, we have negative RA times F times dt. And also for the omega, the rotation of the disk also is counterclockwise. For this reason, omega A is counterclockwise and is positive, minus the initial angular velocity of the disk A times moment of inertia of disk A. The initial angular velocity of the disk A is omega 0 and the rotation is counterclockwise. For this reason is positive. This term is positive. Also, we have to apply the principle of angular impulse and momentum to disk B from time 0 to time F. The only force that makes angular momentum at point B or the center of the disk B is friction force. And the moment that create at the center of mass is clockwise. For this reason, we have negative RB times F times dt. And as you can see, the angular velocity or omega for disk B is clockwise. For this reason, we have to put negative sign here, negative IB times omega B, and the disk B at the time 0 is stationary, and there is no any and the angular velocity is 0. By dividing the equation 1 and equation 2, we find the RA and the relation between RA and RB. Also, from kinematic of rigid body, we learn at the contact point, and two objects has the same velocity. So at the contact point of the disk A and disk B, we have same velocity because we are finding the velocity at time f when the slip ceases. For this reason, RA times omega A equals RB times omega B. Based on the equation 3 and equation 4, we can find the angular velocity of A and B after the time f. And and we find both of them based on the RA, RB, IB, IA, and omega 0. Next example. The information of two gears is given. The mass of gear A is 10 kilogram. The mass of gear B is 50 kilogram. The moment of inertia of gear A and B is given. And the gear A has a moment of 10 Newton meter. And the external moment 10 Newton meter apply on the gear A. Find the angular velocity of gear B is mean omega B after 5 seconds. If the gears start turning from rest, is meaning the omega A and omega B at time 0 is 0. First, we have to draw the free body diagram of both gears. As you can see, we have one external moment applied at the gear A. For this reason, the Ft is applied on the object in opposite direction. The Ft based on the third Newton's law is applied to the gear B at the same magnitude but in the opposite direction. And as you can see, in this external moment cause the rotation at the gear A is a clockwise, and when this force is applied on the gear B, we have rotation as a counterclockwise. And this is the direction of the angular velocity for gear B. Now, based on these two free body diagram and kinetic diagram, we can write the principle of angular impulse and momentum for both of gear. And also from kinematics, we learn at the contact point of the two gear, when there is no any slipping, they have same velocity. So RA times omega A equals RB times omega B. For gear B, the MT is applied clockwise. For this reason, MT is a mass moment times T as a negative sign, and this force is applied in the counterclockwise. Force times T times R, the radius of the gear is positive, plus, and the angular velocity for the gear A is clockwise, and this one is negative. But if we multiply this equation to the negative sign, we got this one. Moment times T minus force times T times RA, or the radius of gear A, equals moment of inertia of gear A times omega A. For gear B, we have the FT, and the FT apply in this direction based on the free body diagram, and make a moment about the point B, or the center of the gear B, as a counterclockwise. We have FT times RB, and also the rotation of the gear B is counterclockwise. For this reason, the omega B is positive. From this equation, we can write the force times T based on the moment of inertia of the gear B and omega B and the radius of gear B. When we put the Ft in this equation, we can find this one. And also from the kinematic equation, omega A equals RB over RA times omega B. By combining this equation and this equation, we found this equation. Also from problems, we know that the moment of inertia of gear A and gear B, after we substitute here, we can find the angular velocity of the B. The angular velocity of gear B is 72.4 radian per second, and this is the angular velocity of A. However, the problem didn't ask us to find the omega A, but we can find the angular velocity of gear A based on this equation, and the angular velocity of gear A is 144 radian per second. Thank you for watching.